Welcome everyone. My name's Mark Hughes and I'm part of the team at Royal Circuits in beautiful Hollister, California and Santa Fe Springs, California. We are the original quick-turn PCB fabrication experts. For the past 15 years, we've been turning out boards in as little as one shift. That's right, we can get your board in about 6 hours if you need it that fast. And if you don't, we can save you a little money if you're willing to wait a few more days. But if you need a board made fast, visit us there. And if you need it assembled fast, check out advancedassemblypcb.com. Our sponsors of the webinar series are Royal Circuits and Advanced Assembly. That's why they get that fabulous plug. And we are joined today for a webinar to talk all about impedance and PCB stackups with Teresa Jensen. But before we get to her, a couple quick housekeeping notes. First, this webinar is being recorded and we will post the recording within 2 business days along with a copy of our slides at royalcircuits.com/blog-2020. As we go through the webinar, please ask any questions in the Q&A section. You'll find that down at the bottom of your screen. Oh, I guess we don't have that slide, but you'll find it down at the bottom of your screen. But please ask them there in Q&A, questions and answers, rather than the chat. It usually gets a little too busy for us to monitor both, so we just keep everything over there. With that, Teresa Jensen has been in this industry for a little over 40 years in one fashion or another. She is one of Royal Circuit's 2 full-time stack-up engineers. Teresa, would you like to tell us a little bit about yourself?
Yes, I started in printed circuit boards manufacturing in 1977. I started out in quality, and a little more than 20 years ago, I went to CAM. So I've been in CAM doing travelers, the actual CAM data, working with the engineers, and now I'm just pretty much primarily doing stack-ups for Royal.
All right, thanks, Teresa. Well, we're very happy to have you with us here today. Thanks for taking the time. As we go through here, we're going to be looking at everything from material considerations to dielectrics to going through a few definitions. You know, if you've ever wondered what TD, TG, DK, DF, all that sort of fun stuff is, we're going to try to cover that here. If you do have any questions as we go through, please feel free to ask and we'll either answer them as we go or at the end of the webinar. All right, so Teresa, you said you're a stack-up engineer and you create travelers. What exactly are those?
Travelers are the specification for on the floor based on what the customer wants. One thing that some people know about printed circuit boards is that we build everything custom. Whereas you say what copper thickness, you say what the finished dielectric is, you say how many layers, and you send us your design and we build it. So no 2 boards are alike. They're not. Even if 2 engineers designed the same board, they wouldn't look the same. Even if they have the same function, it wouldn't look the same, I'm pretty sure.
Oh, I agree with that, Teresa. And as a designer myself, I can design the same thing and I don't design it the same way twice.
Right. You might have different considerations for that.
Yeah, or you have different experiences. You know, the second time you go through it, you've learned more. So yeah, I absolutely believe that. Okay, so the traveler's kind of a recipe then for how you make the board.
Right, for on the manufacturing.
The steps you go through. Okay.
Files to pull for the machines, because CAM people write programs for machines, mostly.
Ah, interesting. All right, so what am I looking at here at this stack-up? Just so we can have a quick rundown before we dive into the details. What are all these colors and all these numbers? What do they all mean?
Well, if you look at on the very left side, that's the layers. We have 1, 2, 3, and 4, and it also says PREPREG and core. And then you have your base copper, and then on the top layers on this particular board, and most boards will have this, is the standard plate, which is a 1 mil, which will give you about 1 ounce, and I'll give you about 1 mil in the hole. And
okay.
So we have 2 different layers of prepreg that you can see on in the middle on the stack up, and a core. And then it shows you the definitions, what resin value and what prepregs they actually are, and DK and DF for those layers, for those prepregs.
Okay, and you're going to teach us what all these things are as we go through, yeah?
I hope so.
All right, thanks. Couple quick questions before we go on. You've been doing this for quite a while. What was it like back in the beginning? Were people using paper and tape, as I've seen in photos?
We used to use Mylar with tape on it, and you had to be careful that the tape, like it might be a pad or a trace, that it didn't come off. When they shot it, they would be like really large. We would shoot them and shrink them down. That was the first process before we had any computer action going on.
Oh, wow. That must have been, I can't only imagine mistakes.
You had to really, you knew what to look for, and you just look for it. I was in quality. So.
Oh, wow.
Even the shoot could be off, you know, where things were too close, or, I mean, it was something to check, and it was so much easier now. And CAM has only allowed us to do more and more and more.
Okay. Hey, I see our other StackUp engineer has joined us. Omar, if you would like to just listen, that's cool. If you'd like to jump in and talk, I'm going to bring you in, and I'll mute you. And then if you decide that you want to jump in on anything, feel free to. All right. Thanks for joining us. At least I think I brought you in. I'm sure we'll find out in a minute. All right. So let's go ahead and move on to the next slide and talk about core and prepreg and what the differences are.
Okay, cores are typically made up of prepregs with copper on the outer layers. And prepreg is an entity all itself. It can be a 106, a 1080. Cores can be made up of any number of prepregs, depending on the size. And yeah, that's pretty much it. It's just prepreg will always not have copper, and cores will have copper, at least on one side.
Okay, and Omar, I do see you. I'm going to unmute you now. It won't let me. Sorry, buddy. We aren't going to have Omar. I also saw when I was doing research for this.
Wrong Omar, sorry.
Oh,
hi, Omar.
Sorry. We're going to wrong Omar. Okay. What are you going to do, Teresa? I'm fired. I also saw online that the cores have a great deal more fiberglass and a whole lot less epoxy than the prepregs. Why is that?
Well, when you lam it, the prepreg, the resin will heat, and it will move around, and it'll fill all the gaps between the traces and whatever you have on your layers, and however much copper you have. And then the lamination press squeezes it, and so some of the resin goes out. So it doesn't keep all the resin. We usually use more resin than we need in a prepreg layer, hopefully.
Interesting. All right. Okay, so all of these dielectrics, all of these things that are making up the board, you know, we've got the fiberglasses, the polyimides, you know, Teflons, all sorts of other things. What's the difference between them, and how do you decide what gets put into a stack-up?
Okay, you know, it depends. Now, the first one you're looking at is 106, and if you notice, that's what they call a spread weave. It's a standard weave, and it has holes. Like, there's going to be resin in there, but like right next to it is a 106.7, and that's a lot more fiberglass. That's called a spread weave, and those are really good for laser, and you can have more lam problems with them. They don't have quite as much resin in them as like a 106. So we use a lot of 106 and 1080s for thick copper. And the spread weave is a good prepreg, but we like it for laser, because the laser is not going to hit one area where it has a hole or it's just resin, and then another area that's fiberglass. So it makes it better for the laser.
Okay, and we should probably define prepreg. Prepreg just means that the fiberglass is pre-impregnated with epoxy resin, correct?
Yeah, correct.
Okay. There's so much jargon in electrical engineering. If we didn't have that, would electrical engineering even exist? I don't know. So you know
Right.
all of these laminates pretty intimately then.
Yes.
How, as a designer, do I know what I need?
Some designers do and some designers don't, but you really want to look at your design. If you have thick copper, you're going to need a high resin. If you have thin copper and you're trying to do a lot of a stacked vias and all that, you might want to use a 1067. But 106 and the 1067 and the 1086 and the 1080, they're all good for, believe it or not, they're good for laser. It's like 2113 and 3313 we don't want to use for laser at all.
Okay, so what I'm hearing from you is
Because it's thicker.
if I have a complex design requirement, what I really want to do is just shoot you an email and
Right.
okay, or talk to maybe like Chris Hunrath
And give
over at
me your
INSULATIVE.
requirements and give me your requirements.
Okay.
I can send you that you can, it'll jog your memory or let you know what we really need and what we'll do if you don't give us information on it. So.
Okay, sounds good.
Or whatever.
All right. Anything else we should know about your dielectric material selections? I mean, I know these are just a few of what we have available to us. I just didn't want to put any more on the screen because it was starting to already get a little busy. Is there anything else you'd like to tell us?
Most manufacturers do make these versions of these or these specific ones like the 106, the 1080, the 2113, the 3313 are very common. And 1067 and 1086 are less common, but most build materials do include these. It's not, different materials have different prepregs.
Is there a big cost difference between these?
You know, the cost is kind of tied up into the thickness. So a 106 is the thinnest, and in this, the 3313 is probably the thickest. So I think the way it works is that if you build it all with 106, it's probably going to cost you the most for the thickness because it's slightly more, but you know, so you sometimes you want to use the bigger pieces, but they're not as good. They don't have as much resin in them either.
Okay, so interesting. Okay, we're getting quite a few questions with these. I'm just going to pick one of these for now, and it says, when we say laser, it says what manufacturing process are we referring to? And we're talking about laser drilled vias, micro vias, Ryan.
Yes, we're talking about micro vias, and they're usually a very shallow drill. They go from maybe one layer to another. We can stack them to get a higher depth. The thing with lasers is that they're actually an angle drill. It's done with a laser drill, and when it hits the bottom pad, it's smaller than it is at the top pad. So we have a rule that it has to be 1-to-1 ratio. As far as like if you have a 6 mil hole, you don't want the dielectric from the top to the bottom to be any bigger than 6.
All right, let's go ahead and move on. Thanks, Teresa.
You're welcome.
So one of the issues that we have to look at is the coefficient of thermal expansion. And the reason for that is that copper constrains the fiberglass. It keeps it from stretching out. Fiberglass is relatively well constrained in the X and Y directions, the in-plane directions, but it's poorly constrained in the out-of-plane directions, the Z-axis direction. So what's really happening is the fiberglass is trying to make the board expand, the copper is trying to pull it back together, and if you let that happen over time, you end up with via cracks, barrel cracks, and separations at the plating where these things join. You end up with all sorts of different types of failures, from open circuits to high resistance short to just, I mean, fire. I mean, we don't want fire, but it could conceivably happen. So you want to have a material that is reasonably well matched from the CTE standpoint to that of copper. Is that ever a concern when you're designing a board, Teresa?
Yes, especially with the laser stack vias, because we're going to lam them. Oh, we lam them like this one that we're looking at right now is a 2 lam process. Well, actually it's 4. Yeah. I don't know. I don't know how they're going to do that one, but I mean, it could be 3 to 4.
Okay, and so when we put this thing into the high temperature press, right? When we put these things together
Right,
to laminate them, it's a hot oil press, high pressure, controlled temperature
right,
press. And if it has to go in 3 or 4 times, that's 3 or 4 huge amounts of stress that you're putting on these things.
right.
So,
It's heat and pressure. And we usually will ask our vendor what material they have that can withstand X amount of lambs.
okay.
All materials can do that, can go through 4 lambs or 5 lambs.
All right.
Processes.
Question is, do we make boards with more exotic RF dielectrics? I assume that's things, you know, like Teflon, that sort of thing. We absolutely do. We're just not covering them in this particular webinar, but we do that, you know, every day. We're doing stuff, RF, microwave. We're just
Right.
not really looking at that in this particular webinar. Those dielectrics are really nice because they're consistent. Fiberglass dielectrics are anisotropic, right? They have different material properties in each axis, in each direction. But some of these more exotic ones like Teflon and what, they don't. They're isotropic, which makes them a lot easier to work with from a design standpoint, but from a material standpoint, they're a little harder to fab.
From a manufacturing.
Yeah, the Teflon doesn't like to stick to the copper, so that can become an issue. We're just not covering that in this webinar at this time. And the same thing with the polyimides, we're just kind of skipping over it for now.
It's a really soft material too.
Yeah. And we do
a lot about flexible materials.
Yeah. And we do ceramic impregnations as well, right?
Yes, we do a lot of Rogers. That's the ceramic is Rogers.
Okay. All right. So yes, if you have those, we do them. We're just, the webinar is already kind of stretched for time, so we don't want to get too many. All right, so glass transition temperature, TG, is the temperature at which the fiberglass kind of goes from this solid, you know, material that's strong to kind of this rubbery concoction that you can, you know, think of it like silly putty, right? It's the temperature at which this stuff starts to move from solid to liquid. It's not liquid, it's just a really amorphous solid. It can be moved around a little bit. And the issue that you have is that when you're trying to assemble your board, if you've got a low TG, your board can actually start to warp and bend while it's going through the reflow ovens, and that can be bad. So TG is something that you often want to look for, especially when doing the ROUGHNESS compliant, the lead-free solder. So that's just one of the many jargon terms that we have. And we've also got this thing called decomposition temperature, and this is the temperature at which the fiberglass resin mixture loses about 5% of its mass, and it really just starts falling off. This is the point at which it basically just starts sublimating or being squeezed out the side of the board. Did you want to tell me about that real quick, Teresa?
Yeah. Well, this says irreparable damage occurs at these temperatures. So, I mean, if you put your phone in the oven, it's not going to work. But yeah, so you lose copper adhesion, and I've seen boards that have been burned in ovens, like in manufacturing before, and they literally just dry out.
Yeah.
And then nothing holds together.
You do get a little bit of damage in the multiple lamb cycles, the multiple lamination cycles. There's always a little bit of damage. That's why you can only let these things be laminated a certain number of times, you know, some of these materials. So it can be irreparable, but that doesn't mean that it's a game change or a deal breaker, right? You can still potentially work with the board at that point.
But these temperatures are Celsius, so these are really high temperatures.
Yeah.
So,
but sometimes
whereas just to get it to flow, I mean, that's good for us when we're laminating, and then this is like you've just destroyed the board.
Yeah. Which most people.
And it's telling you at what point it will do that.
Yeah. So anyways, that's your decomposition temperature, your DK. We've also got the K, which is the thermal conduction. And a lot of these boards are somewhere in the range of about 0.4 watts per meter Kelvin. Copper, on the other hand, is somewhere near 400 watts per meter Kelvin. You can get you can get materials that are thermally conductive to allow you to transfer greater amounts of heat. But really what it comes down to is that if you've got thin layers and you've got a bunch of heat on, say, layer 2, it's going to get to layer 1. It's going to transfer along the copper. That is your best conductor and your best way to move heat around your board, rather than trying to move it off axis through the dielectrics. Anything you want to add there?
No, that sounds good. I mean, yeah.
Okay. We've got a few questions here, and one of them I'm going to address, the rest I'm going to sit on for a little bit. How would one know if they have TG, glass transition temperature issues?
How would you?
So how would a designer know if that is something they need to worry about when they spec out a board?
I think you need to understand like what operating, what your board's supposed to in operation. I mean, some boards are exposed to heat just from running, so you need to know what that is, right? And then of course your solder, reflow, whatever, however they're going to insert their components and then add the solder to it. That also is a consideration. And you know, lamination is kind of what we don't even worry about that. We follow the recipes.
Yeah. So to answer your question, Drew, the two concerns are assembly temperature and your operating temperature. So if you look at your data sheets and they tell you that, you know, such thing needs to be soldered at, let's say, I'm just going to make up a relatively high number, let's say 290 degrees Celsius, which is about, you know, 50 degrees higher than I would expect. Then you might want to keep an eye out for the transition temperatures of your boards. But other than that, you probably don't have to worry about it unless you're doing some harsh environment, downhole type stuff where, you know, the environment gets really hot. You probably don't need to worry about it as a regular designer. Perhaps if you're doing something that has a lot of gates, a logic circuit, and FPGA, and you don't have good thermal conduction, maybe, but maybe. And then Sean says, so can FR4 work at 200 degrees Celsius? Sean, FR4 is a broad category. It just stands for the flame resistance or flame retardant level of a board. And there are hundreds of dielectrics that fit into that category. So it would depend on which one you chose.
And
all right.
They're very seldom lower than like 170 and 180 TG. Most materials run around 220 to 260. So, and you know, it might sound like an odd thing for you, but you can contact people like Asola. You can contact any of these vendors for materials that and talk to them, and they have great answers for your questions too. I mean, they're good sources. They're the experts on their material.
Okay. Let's go ahead and move on to our next slide then. So one of the other things that engineers talk about all the time is decay, which is your dielectric constant or your relative permittivity. It's a ratio of the permittivity of the material in a medium to vacuum permittivity. So how much energy can we store in the electric field that is going to exist between two copper traces in that board? That's really what it comes down to. How easy is it to generate a field? How easy is it for that field to dissipate and give us energy back into our thing? And it comes down to how many polarizable atoms and molecules are in there, and how much can we polarize them? And for boards, it turns out that it decreases pretty, I'm sorry, wrong thing. So for boards, this depends mostly on what the dielectric is, what the dielectric medium is inside the board. The dissipation factor, how much energy we're going to turn, you know, as we're creating those fields and letting those fields dissipate, they're going to generate heat. And how much heat is generated is going to depend on the frequency and how the board is made. So DF is the other big one, the other jargon term. And mostly when engineers spec out boards, they will go to Teresa and say, hey, I either need X and X, you know, DK, I need it to be this value, or they will give her a slash sheet, or they will call out a material specifically. Is that correct?
Yes, that's correct. Sometimes they'll just call out FR4, and if they do, we stock some materials, so we'll just probably use 370HR or TD or 1HR material.
Okay, thanks.
And that's the cheapest way to go too, by the way.
Repeat that then. I
I
heard
would like
cheap.
to say something about this. I do get a lot of questions from engineers, and I would like to say, as far as the DK goes, when you look at a slash sheet, it'll say at the top of it, DK 3.44, you know, whatever. And if you find the DKDF sheets, which is a different format, it will break it down. It'll tell you a 3 mil core has this much DK. So DK values change. So if you're using an inexpensive or free software online, you might want to get some of those slash sheets that tell you specifically what the DK is, and you'll be a little more accurate in your readings.
Okay, and just for, if I remember correctly, the DK of epoxy is much less than the DK of fiberglass. So as we're moving through the material, it's not a constant number, is it?
No, it's not. And it tends to be the thicker they are, the higher the DK. So, you know, that's the way it tends to be. Yeah.
Interesting. Okay. So DK is the dielectric constant. Basically, how much energy can I store in the electric fields that exist between, you know, two pieces of copper, and DF is how much energy am I going to lose as I'm doing that storage? How much of that energy is going to be turned into heat and dissipated into the board itself? Do designers worry about DF as much as DK?
No, not as far as I know. I mean, no.
There's not much you can do
I
about.
think it depends on the designer and how designers that are very, very picky and they want all the ducks in a row. And I talk to designers that are like, hey, I want this, thanks, great. And that's the last I hear of it until they order their boards.
Wow, okay.
So.
All right, so as we were mentioning a second ago, it's different numbers. So if you're using a very open weave, as your signal propagates in the electric fields that follow a trace, the area in between is going to be full of epoxy resin, where the dielectric constant is lower, and then as it travels and it hits the fiberglass, it's going to be higher, lower, higher, lower, higher, lower, higher. Every time that it changes, a little bit of your signal is going to be reflected back, a little bit of it's going to be absorbed, most of it's going to transmit. So if you have a high-speed design, really what you're looking at is something with a tight weave, so that you've got less epoxy, more fiberglass, and a more consistent dielectric constant. That'll give you a more consistent impedance as your signal travels. So something to keep in mind when you're creating these things is the prepregs have a lot of epoxy. Cores don't. So you usually want your signals to travel and be coupled between adjacent layers on a core, rather than, you know, if you're doing a cap construction or something like that. Would you agree with that, Teresa?
Yes. Yes, I will.
Okay, well then, now that we've got that behind us, let's keep going. So, you know, oftentimes you hear people talking about conductors, but really the only material that boards are made of these days is copper. It's got the highest thermal and electrical conductivity of any metal other than silver. Silver is more expensive, and it turns out that it's harder to work with. So copper ends up being pretty much the best thing to use. You'll see gold next in line down here, and people are thinking, well, you know, well, why do we put gold on boards if it's not as great a thermal or electrical conductor? And the answer for that is gold won't oxidize, copper will. And oxidized copper is a poor conductor of electricity. So we put gold on, you know, interfacial surfaces to prevent that from happening. Anything you want to add there?
Years ago, all the boards were gold. They made them with gold. That was the deal many, many years ago. And then they went to copper because it's cheaper, but gold is a pretty good conductor. And we plate two different types of gold. One is a soft gold and one is a hard gold.
Okay, and are those our ENIG and ENIPIG processes?
Yeah.
All right.
And we also do go for connectors, fingers, connectors. Whether
Good.
into a connector, there's usually gold there.
Good, good to hear. All right, copper is what we're using these days though. And copper's got different properties like roughness. We create copper in two different ways, and I think we talk about that in the next slide. But depending on how we create it, it can be either pretty smooth or pretty rough. Now I know what you're thinking, well, why don't we just make smooth copper everything? And the answer is because smooth copper won't adhere to the fiberglass and epoxy resins that sit below. So you need some amount of surface roughness, otherwise the copper is going to peel right off your board. Trouble with that is surface roughness increases the dissipation of your signal as it propagates along the lines. So if we look down here, you can see 2 parts of copper foil. I don't really know how this was made, but if I had to guess, I would suspect this. Well, actually, you know something? I'm not going to guess, not on a thing. But we've got one part of the foil that's very, very smooth and the other part that's very, very rough. If you were going to send a copper signal down this, you would probably want the electric field coupled on the top side of this with another smooth piece over here to reduce the amount of dissipation that you have. So copper's made in 2 ways, rolled annealed and electrodeposited. Rolled annealed, there's a drum and it's just accumulated on the drum, and as the drum rolls it's pulled off, so you get a nice smooth side and then you get a rough side. The rough side is great for attaching to prepreg. The drum side is great for attaching your electric field lines. This is where you want your signal to go down. As you pick out your copper, if you are doing high-speed stuff, you might want to use a low profile or very low profile. Do you want to tell us a little bit about those and the processing that we do for those, Teresa?
The processing for low profile?
Well, don't we have special handling considerations?
We do, because honestly, when we pull material, scrub it before we do anything. And it's part of it is like to prevent oxidation and also to have that tooth. But with the VLP, which is a very low profile, we don't scrub them. We will do a chemical clean.
Okay.
Or hand scrub, like gently. Yeah.
Yeah.
We can't scrub them like we normally would in a high-end scrubber.
Yeah, and for those of you that are wondering, the reason that we have to, that we want smooth sides and, rough sides, again, rough side is an adhesion, a material fabrication requirement. Smooth is a signal integrity requirement. Right. And as you have a conductor, you get this thing called the skin effect. You have eddy currents that get set up in high frequency conductors that actually increase the resistance towards the center of the conductor, forcing the majority of the transmission to exist on the outer layers, on the periphery of it. Well, when you get up to about 100 megahertz and certainly to a gigahertz and whatever, almost all of your signal is traveling on the surface of the conductor, which might be quite rough. All right, so that's going to increase your dissipation factor. So the VLP is what you need when you're up here at 10 to the 9 hertz, when you're up here at a gigahertz. That's when you need to start worrying about what kind of foil that you're getting. These real high speed, the RF, the microwave certainly, you might want to look at what conductor that you're calling out in your specification, as well as what dielectric you're calling out in your specification. All right, now on to the exciting stuff. How thick of copper do we get? At Royal Circuits, I mean, we'll play with anything for you. And we've actually recently updated our minimum trace and space numbers. Before I talk about this heavy copper real quick, these are our absolute manufacturing minimums. You want to call out traces and spaces higher than this if you can. When you're down at the minimums, our yields are going to go down, which means we're going to have to make more copies of your board to make sure that we're able to deliver enough to you. That means more risk for us, so more cost for you. If you can exceed the minimums due, it will decrease your cost. All right, for those of you out there that are designing with heavy copper, you probably maybe not, but you probably use an online calculator, and online calculators are almost exclusively referencing IPC 2221, which is an outdated standard that was developed by two guys in the 50s and somehow survived through the years. It's bad. IPC 2152 replaced it. It's still very, very conservative, but it is at least empirically derived. So two guys, Drs. Douglas Brooke and Johannes Adams, went through and they took the data from IPC 2152 and they developed an equation for it. This particular equation only works for surface traces at standard temperatures and pressures, right? 20 degrees Celsius, atmospheric pressure. If you're dealing with Denver, Colorado, you would need a different multiplier up here. If you're dealing with subsurface traces, something closer to the core, you need a different number up there. We've got whole articles on it. If you visit either one of our blogs, you should be able to stumble upon it. But anyhow, here's what we did. We rearranged the results of Dr. Brooke and Adams' study, and we did it for just a few common copper weights. We came up with a couple of graphs and charts at a bunch of different delta T's that are allowable. Say you're allowing a temperature increase of 15 degrees above ambient, above 20. You're letting your board get up to 35. Okay, that's great. And you want to know what copper weight and what copper trace thickness you have for, say, a 5 amp current, which is a lot of current. All right, well, if I have a 4 ounce copper, I would need a trace that is about 50 mils wide. All right, that's not too bad. I would need some heavy copper, but it's not a big deal. What if I tried to run 5 amps of current through a 1/2 ounce copper? Well, 1/2 ounce copper is up here. I would need upwards of 300, 400 mils to carry that. So these charts, and again, you can find them at our blogs, these charts just kind of let you eyeball and get a good estimate of what copper thickness and width that you will need for your trace. Anyhow, that's something that you're going to have to spec out to Teresa too. We don't do these calculations for you. You're the engineer, you have to figure it out, but we do provide these to you as at least a jumping off point.
And also I'd like to say 0.25 ounce does come in foil, but not cores. 1/2 ounce is what we use for the minimum for cores.
Yeah, okay, so yeah, the 1/4 ounce, and you can only get that in ED, is that correct?
Yeah, in foil, yeah.
Yeah, I don't think they create rolled annealed that's quite that thin. All
yeah,
right,
that would be a messy process. And copper. Yeah.
Okay, so a couple quick questions that we'll address before we move on into talking about the software that we use. When we're using VLP and we plate, does it change the smoothness? It absolutely does, Jimmy. If you plate a very low profile, you're not going to have VLP anymore. Very sad. Other questions. Is it true that the glass weave skew effect can be mitigated by spread glass? Yes. It will help. It doesn't remove it entirely, but it should help substantially. If you're choosing the flat glass, e-glass, it should be a little bit better. Ernest asked, is there a formula for internal traces? Ernest, it's the same formula with a different constant. So that 215.3 changes. If you visit our blogs, there should be a link to Dr. Douglas Brooks and Johannes Adams' book. And Dr. Brooks has the article, the chapter from his book that specifically addresses traces for free on his website, ultracad.com. So you can save a couple bucks if you just kind of want to get a thing. We've got questions. Teresa, we brought up the term slash sheet earlier, and we've got some questions on what a slash sheet is.
That's a data sheet, really. The data sheet is, there's a data sheet that gives you the overall, all the specs on the material itself, PK, the CTE, the TG, TD, DF, all, and more. And then they might tell you what types of thicknesses they have for the cores and what types of prepregs. Some manufacturers do it a little differently. Some are real simple, some are more complex, but it gives you an overall view of what you can buy with that material as far as thicknesses and what the specs are. But the DKDF sheets are a different thing. That's just a sheet that shows you all the different cores and all the different prepregs and some combos of prepregs and tells you what the DKDF is for those.
Do you remember the IPC standard that uses the slash sheets where those are generated off the top of your head? I don't.
No.
Okay, so there's so Mike, there's an IPC standard, and I don't really remember what number it is. 61 something, I don't know.
Yeah.
Anyhow, at the end of that standard, there's a whole appendix of numbers. You know, so it'll be IPC standard something 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 slash 200, and that 200 gives the material property specifications that we would then go find a manufacturer and core that matched those specifications. That's really what it's coming down to too. So,
right.
Anyhow,
Okay.
IPC 4101, that very well could be it, Mike. There are so many IPC standards out there, I just don't remember. But 4101 sounds familiar to me. So if I had to guess, I would say that's a good place.
I think that is right, 4101, and then it has a slash 2411.
Yeah, that sounds right.
Yeah, 4101.
Yeah. We've got other people chiming in. It is 4101, so I'm going to believe you guys. It sounds right. It's just there's so many. I see so many IPC standards in my daily work that I don't even know which one's which anymore. It's okay. Do you prefer your fab drawings calling out slash sheets, or what would you prefer people give you?
You know, they can just call out the material itself. You know, whether it's Nelco's and 4000-13 EP or FR4, some people call out FR4, and they can do either one, and we'll find the material for them.
Okay. All right. Well, tell us then a little bit more about your job. Tell us how you go about creating a stack up for a customer.
Well, what the actual software itself, this is like my first screen where I'm going to assign the amount of layers, the type of build, whether it's core or cap or foil, and the type of material, the overall thickness, and the solder mask, and then the colors, and sometimes the colors and the type of solder mask, and then the silk screen, how many layers it's on, and what color it is or type.
Okay. What's the difference between the two different types of build types again?
Oh, foil and cap. So cap construction has a core on the top. I think they might call, some people call it cap, some people call it core, but it has a core on the top, and then it would have prepreg after layer 2. And then the foil has foil and then prepreg and then a core, typically.
Okay. So this is your first screen. So we've called out a 4-layer foil that we want 62 mils thick, which is a pretty standard. That's 1.6 millimeters. That's pretty standard.
Right. Yeah, and it just that. The other thing is that my software also keeps everything symmetrical unless I tell it not to. And that little arrow, that little triangles, 2 triangles on the top is what tells you to either keep it symmetrical or not. Symmetry is important for warpage. But anyway, here I assign the layer types, and I would do signal, mixed, or plain. And that defines the copper area somewhat, you know. And later, when we actually cam the order, we can pull in the actual specific numbers of copper square footage on each layer in the panel, and that affects the impedance. That also can affect the thickness.
Okay, your audio
slightly. It can change slightly.
Your audio cut out there when you were saying something very important, and
okay,
that's related. Sorry. No, it's not it's fine. I just want to make sure our participants hear this. Symmetry is incredibly important in board stackups. If you create an asymmetric stackup, which by the way we can do, and we have some customers demand it or require it for whatever reason, the issue is due to the varying coefficients of thermal expansion and the varying stack up, you know, if it's not symmetrical about the midline, the midplane, it will warp during assembly. it turns into a potato chip, or it turns into a curl, a curve. I mean, it can take lots of different shapes. But
It can do
something
that
people,
coming out of lamb.
yeah, it can do it. But I mean,
Yeah.
John's going to fix that. He's not going to ship it off to assembly board.
Right. Yeah,
But
exactly.
once it gets to assembly, it might not stay that way. So something people do realize, most engineers realize the importance of a balanced stack up. However, here's where you can go wrong. As you start routing your traces and you start taking copper away, if you don't use copper pores or copper thieving, your board might have started out with even amounts of copper and dielectric on each side, but it might end up with different amounts of copper and dielectric on each side. Or a lot of you out there like routing, say, horizontally on odd layers and then vertically on even layers, right? Just for your high density interconnect design. Well, you've now created an unbalanced stack up. It's not just the amount of copper that you have on, it's the copper direction. Copper constrains expansion, right? If you have it constraining it horizontally in one direction and vertically in another, well, this thing's going to warp like a Pringles chip. It's called a hyperbolic paraboloid. So just something to keep in mind too. Anyhow.
And remember that the amount of copper, thickness of the copper affects it too.
Say that again.
Stability it provides or not.
All right, next. This is your next screen.
Yes, so now I consider myself in the actual job. So here you can add drills, and this gives you the information as to whether or not if you've met your thickness. And I put in the information for the customer and etc.
Okay.
For the drills, where I lay out the drills. And then here's the stack up, similar to what you would see, but there's a little more. I can add plating. Again, if you look at where it says plating, a little towards the right side, it says standard for the outer layers, like I said before, where we always plate the outer layers when we plate the holes, because if we didn't, you wouldn't like your holes very much when they separated from your base copper. But so we plate over onto the pad and we plate all the traces. And then custom plating is for any laser, any subs, any blind or buried. And a totally buried layer, we would typically add our standard plating to that, which would be 1.2 mils. And if you want your layer, if you want those holes to have a little less copper, if it's okay for you, then that would give you less copper on that layer also. Something to think about. Because when we plate those, it's just like an outer layer. We plate the surface too.
All right. Do you have people ever come to you with an odd layer stack up, like 3 or 5 layer?
Yes. Yes.
Frequently?
Not infrequently, but I mean, I do them. A lot of times we'll even them out and we'll add a blank layer in there and, you know, try to, so we can match all the dielectrics.
Okay.
So, I mean, it's not a big deal. A lot of times we don't build it so that it's, well, we try to get it as symmetrical as possible, but we can build a 5 layer.
Okay. What are we looking at here?
This is the impedance page. So on this one, this is kind of an interesting one, but we have a single-ended differential and then coplanar, single-ended and coplanar differential. And this one is single-ended coplanar. So we have a space to the ground where it says space and then in parentheses it says ground. And then we pick there's a design width, line width, and an actual line width. Now, if you sent me a request and you said, I want this dielectric, or I just want a board with these layers in it, and it has to be overall thickness, and I pick it, I will say design width and actual line width will be the same. But if you tell me that you want a 5 mil trace and I have to make it a 4.3 to make it work, or a 5.6 to make it work, the actual line width is the line width that the program uses to come up with the predicted ohms on the right here.
And it looks like in the red there, they are way off of target.
Yeah, yeah, this is an actual customer who's probably not going to understand why. I just built it the way they wanted it, and I couldn't even find those traces, so I left them that way. But normally I would fix that, but I just built it the way they said, and have them advise what to do on it.
Interesting. Now, we offer free impedance calc and STACKUP at the quote stage, right? You don't have to pay any money for us to tell you
Nope.
how you should design your board.
No, you don't.
That's a
Yeah, I'm working with you. It's not that I'm telling you how to do it. I can tell you if what you want will work, or what would be the best way to get what you want. But most engineers do know what they want and how to get it. I mean, even if you're using a free online software, you can get pretty close if you're savvy about it, and make sure that your decays are right and pay attention to what you're doing and fill in the blanks. You know, software like I have, it kind of helps you solve the problem. But when you are using a free one, you have to fill in all the blanks.
Yeah. And there's a lot.
And there's a lot to it.
And a lot more room for error. Might as well just let us do it, especially if it's free.
Right. It's easier for me. And the reason it's easier for me is because I have this beautiful little thing right here. And what it does is, if I don't have the right impedance predicted ohms, I can do a thing called back calculate. That's this little screen here. And it will give me the line width, or if I choose the spacing, if it's a differential, and the line and space. So it could give me both of them, or the actual dielectric between the layers. So it'll tell me what I should do. So it helps me from getting lost trying to put in different prepregs to make it work or whatever. It'll tell me exactly what I need. So I know how far off I am, and I know what I need to do to get there. And typically I will try to move the dielectric unless the customer doesn't want that. And I'll try to move the dielectric first and then tweak the line width.
Okay.
Style.
So here we've got a sample, and we've got sample stacks at our website, royalcircuits.com, under our resources, I believe. But here's a sample. What are we looking at here?
This is a simple 4-layer board, foil construction, 1 ounce copper finish. It's a pretty basic board. 106 and 180, 1080 material, and prepregs and 039.
Okay, so
standard.
From a cost standpoint, every lamination cycle increases the cost of your board, right? Here,
right.
You and I are looking at this, and we know that this is going to be done in a single lamination, but our customers don't. How do they know how many lambs something's going to take?
We will do more lambs based on the drill structures. You know, blind and bury vias, especially when you're doing, like, let's say you have 10 layers and you're going to drill, you want to drill to go through 1 to 2, 2 to 3, 3 to 4, 4 to 5, and throughout the whole stack. Then we'll start from the middle and we'll drill the core, and then we'll and plate it, and then we'll start adding prepreg and do a laser, and then add some more prepreg and do another laser. That's when you get into the high lambs. And when you have different drills, like if you have a 1 to 3 and a 5 to 6 and a 4 to 6, it depends on how we want to do it, what size the drills are, how thick the dielectric is, if we can do laser, or if we have to just do a sub and drill the 1 to 3 and run it through plating or not.
All right. And then what's next? And then we'll get into some questions here in just a second.
Okay.
So this was one of the slides you sent me that had a very complex stack up, and then I also added in your other images here at the bottom right.
Yeah, I wanted to show this one. This is a, we have different reports that we can give. And one of the reports on the bottom right, this little has two single-ended and a differential on layer 3. And this one has a lot more information. It has the inductance, the conductance, the attenuation, propagation, delay, and capacitance. So, I mean, for me, I can print that one for you, and it's in the data. You just have to ask me for it because I don't remember who wants what. But if you want that type of information and you need that, definitely ask me and I'll give it to you. It's an impedance detail report.
Interesting. I didn't even know we had that. Very cool. And that's, if you take a look at the shape of the trace, that's another reason a lot of online impedance calculators are wrong. They don't take into account the significance of fringe effects for these very thin, small traces. And the fact that these things don't etch straight down, they etch at an angle. So just...
They kind of etch from the sides.
Yeah, they create these little trapezoids. So take us up on our offer of free, all this information is free at the beginning of your design or at the end of your design, but take us up on it. All right, here is one last sample stack up of a rigid flex that I stole from Omar. But here you've got an example of all sorts of these different exotic materials that we can interject into your boards for you. If you need a flex, a rigid flex, or a rigid stack up, anything, we're happy to help you, and it's free at the design stage. With that, let's jump into as many questions as we can stomach before lunchtime. What do you say?
Okay.
All right, there's all sorts of them. Do you happen to know the copper thickness in via holes for IPC class 2, the minimum copper thickness?
And the via holes?
Yeah.
Class 2?
Yeah.
I think it's 1 mil. And I think there's a tolerance on that of maybe, it depends on how many pinholes, and I don't remember it specifically, but I think it's 1 mil.
Yeah, I don't really remember.
For class 1 and 1.2 for class 3.
So, and if you need us to drill down on that for you for a specific reason, that's something I can look up for you very easily, Ray. It's just also very easy to misremember it off the top of your head. But if that's something
if I'm not looking at it, there are different factors though. So there's like voids or pinholes and things like that for the different classes too. It's not just the thickness.
Yeah. So if that's something you really need to know, just shoot me an email, mhughes@aapcb.com. I can look that up for you in about 5 seconds. What weave is most suitable for high-speed digital or wireless designs versus some general circuitry? And does the weave pattern matter when measuring nanoamps from a sensor?
I don't know the answer to that.
So depending on, when you say high speed, that means something different to everybody, Mike. Some people think high speed is anything over 100 megahertz. Some people think high speed is 20 gigahertz. Shoot us a specific question through email and we can help you out with that. Does the weave pattern matter with very sensitive electronics? Measuring nanoamps, I don't know that it would. It would depend on your specific application. We might actually need to be looking at the resistivity of the board and the solder mask before we start looking at weave pattern. It's really a specific question, so shoot us an email. We'll try to do that for you. How to calculate the number of laminations. It depends on how many vias that you have, as well as how many layers that you have. We're going to have to image the construction. If we're laminating a bunch of cores, we're going to image the cores before we laminate them together. If we're doing foil on core, every time you add a layer of foil, you got to lam. Add a layer of foil, you got to lam. And it's not that we can't laminate multiple layers of foil at once, it's that you have to image them. And once they are laminated, you can no longer image them. So.
And you can't etch a piece of foil.
So.
To have it on something before you can do that.
Yeah. Why is thinner dielectric layer cheaper? I think we said that the thinner dielectric layers were more expensive than the thicker ones.
They're cheaper, but when you have to get the same amount of thickness, it could end up being, because it's kind of hard to explain, but
You would need more of them, right?
pieces, the biggest pieces for the amount of thickness that they have are a little cheaper than if you've built it with 106s, you know, the smallest. If that
So,
makes sense.
yeah, so Hong, I think we're talking about two different things here. If you need a
Oh.
desired thickness, right? Let's say you want a 1.6 mil board. You know, that's what 1.6 millimeter, 62 mil
Yeah.
board. And you're trying to stack that up out of, you know, 50 sheets of 1 mil dielectric. It's going to end up being expensive because you're using many more sheets of this fiberglass versus, you know, a couple thin sheets and one thick sheet, if that makes sense. So it's that we would be using more material overall, more surface area to create that volume. So
Yeah, it's not a huge price difference. It's just, it is a little bit more when you use thinner dielectrics to create the same thickness.
what is the minimum TG for a lead-free process? What's the minimum glass transition temperature that we should pick?
The minimum?
Yeah.
I think it should be, I think it should be 200.
Something like that, yeah. So
Yeah,
somebody asked
200.
about 170, and that just feels too low to me.
Yeah.
So, okay. Is the lead-free solder joint relatively more brittle than leaded solder joint? Yes, but everything's ROHS compliant these days, so you got to roll with the flow. Drew, I don't know if I completely understand your question. It says, so a high TG substrate would be like 170 or 180, but lead-free would be something like 220. Wouldn't that exceed the glass transition temp? I don't know that I fully understand your question, buddy. Yeah, you would want a higher TG. TG is the glass transition temperature. You want a higher TG for lead-free. I think maybe one of us misspoke and confused you. Your question, so I'm sorry, buddy. How do I calculate overall decay if we've got multiple prepreg and core? What calculator do you recommend? The best thing that you can do, Henry, is let us calculate it for you. All of our data, you know, once we create a target impedance, right, we will fabricate that board and then we will generate an impedance coupon that we will then measure it against. We get to feed that information back into our system so we can constantly improve our process. So our target impedances are, you know, tenths or hundredths of a percent away from our predicted impedances, just because we can constantly refine our measurements. Those online calculators that you find can't do that. How do you find the decay in an ISOLA data sheet? It should be listed. ISOLA's got all their data sheets online. Check out INSULATIVE.
I'd like to speak on that.
Sure.
On the data sheet, it usually has an overall, it'll say 3.44, 3.8, whatever. But the different dielectrics are on your DKDF sheets, and you can manufacture for those. You know, you can go to their website and make a request, or actually find them on their website. But they have DKDFs are different for a 106 prepreg than they are for a 7628, which is a lot thicker.
So Jimmy just asked, so what would be the best option for plating for high frequency signals? So Jimmy, what you want to do on a high frequency signal, if you can, is keep the signal, the field lines confined between the dielectric on a core material, right? It's okay if the outer surface of that signal is a little bit rough. You want the inside of it to be smooth. That's the part where you want the signal to propagate along. You want the field lines coupled on the interior of that core, not radiating out into space. As far as plating goes, we do use pulse plate, which gives us a relatively smooth surface at the end. It's not great, but if you've got the drum side of your foil on, you know, that's the part where the signal's propagating, that's really what you want to go for. And I don't know if I explained that well, but shoot me an email at mhughes@aapcb.com and I can send some pictures over that might explain that. What is your recommendation for pitch and bump size in PCB fab processing supporting high voltage circuitry in BGA and other die to prevent arcing? That's a lot of questions in one, anonymous attendee, and you'll have to shoot me an email for me to follow up with you on that since I don't have your contact info. But anywhere between 800 and, I don't know, 1200 volts per mil is the breakdown voltage of these dielectric layers. And the minimum thickness that we usually put is, say, you know, I don't know, 300 mils, something like that. So arcing between layers is a concern mostly at that point from an ESD standpoint rather than a circuitry standpoint. But you can look at the breakdown voltages of these dielectrics when you look at their specification sheets, their data sheets. Minimum pitch and bump size in PCB fab processing. I mean, do we know the creepage and clearance stuff off the top of our heads? I don't. Do you?
Mm-mm.
Yeah. We would have to follow up with you, but since you're anonymous, we don't have any way to do that. You'll have to shoot us an email. Can we do odd numbers of copper layers? We can. We don't recommend it. What are the pros? There really are none. It's just a whole lot of cons.
If we can make it symmetrical though, as far as the dielectrics, it's not a problem. You know, just consider the dielectrics and, you know, what cores you're using at the top versus the bottom, and, you know, the dielectrics for that should be fine. We can make it work.
Yeah.
Do it all the time. We do.
How does this STACKUP software compare to the Allegro STACKUP setup?
I love this software, by the way, but I don't know. I've never used Allegro.
Yeah, this is
that I use.
Yeah, this is bespoke software. This is made just for Royal Circuits. We've got a company that that works on it for us.
Some of these reports, I've requested these reports. So, I mean, the person who designed the software is very user-friendly and helps us on anything that we need for our customers.
What are the advantages of odd layer stackups?
Odd layer stackups?
Yeah, these 3 and 5 layers, are there any?
Not for us.
Yeah. From a design standpoint, I can give you an example of when I've seen something like that. A designer goes out and they make a 4-layer whatever board, you know, and it works out great. And then they decide that they need to turn their rigid board into a rigid flex board. So at that point, they decide to start inserting layers for the flex layer, and it goes odd, you know, in a fraction of a second because they don't want to redesign everything else. They just want to add a layer. Okay, you know, I've seen odd stackups generated that way. I don't know that I've really seen anybody go out and generate one from scratch, or at least I'm not saying it doesn't happen. I'm just saying I haven't seen it. What else? Is acid trapping a critical issue? What's the worst case routing angle where acid trapping is a critical issue? Jelani, that used to be an issue with old fab processes. That's really not an issue anymore. So you're talking about acute angles. You know, don't route, you know, where the internal angle's 45 or something like that. It doesn't really matter anymore, for us anyway. Can't speak for other fabricators, but we don't really care. Would you recommend leaving solder mask not covering controlled impedance traces? That is a tough one. It's going to depend on your speed grant. Mostly I would say cover it, but for the real high speed stuff, man, it even matters what color solder mask you use, I've heard, because
what type of solder mask, yeah.
So it depends on how really, if you're getting into the weeds on that type of stuff, yeah, it matters. At the real high speed signals or the real fast transitions.
And solder mask has a decay value.
Yeah. Why is silk screen 0.00 thick? It does have some thickness, right? Yes, it does have some thickness.
In places.
Yeah.
Not
okay. When is the best time to get you involved in the impedance conversation?
Anytime you need impedance, you know, and you want to build something with Royal Circuits, you can shoot me an email. And I mean, if it's really complex, I'll call you and talk to you. But if you could just send the information on the email, I can come up with a stack up for you, and I can give you advice too. I like doing that.
Oh, I've got a mistake on your email, Teresa. Somebody just pointed out it's royalcircuits.com, not Royal Circuits. C-U-R-C-I-R-C-U-I-T-S.
on my email? Oh my gosh. Well, thank you.
Yeah, thank you for that. Okay, I'm only going to take one or two more questions. We need to get Teresa back to work here. What is an impedance coupon? So when we make panels, these things, and I'm sorry, this is just bugging me. I'm getting itchy. I have to fix this, Teresa. I have to fix your thing. Would you tell us what an impedance coupon is while I bring your email up
Okay,
and correct it?
an impedance coupon is a coupon that we build that is placed on the board outside of where the boards are themselves. So typically the traces are, I think, 5 to 6 inches long, and it gives you the impedance, and it gives you the impedance. You can test it, or we can test it, and we test them all anyway. But you can test them all yourself because we send them to you.
Okay, Grant asks why are
and we
stacked.
charge for that, huh?
So Grant asked, why are stacked microvias more prone to failure than staggered? It really depends on how your manufacturer makes those microvias. If they don't do good cleaning, good desmearing, then you can't, my understanding anyway, is that you tend to get more failure in the stacked. Mostly, I believe it's due to the way that partly the way that the plating happens too. But if you start drilling into plating and drilling into plating and drilling into plating, you run into more trouble than if you're drilling into foil and then moving over and drilling into foil and moving over and drilling into foil. That's my understanding anyway. So it just depends on how clean your fabricator is. You know, your cell phone, you know, might be a 20-layer board and they're all stacked because there's no room for staggered. It's just going to depend. I'd really have to pull out some research to be able to tell you more about that. All right. Let's do one more. We did impedance coupon, and then we will follow up with anybody else. If you want to email us, we're happy to answer it. Can you tell us when we've got quite a few on this. When do we use soft gold and hard gold?
They were gonna ask me that. You know, not a while ago, I got into a discussion with someone about that, and they were wrong and I was right. And now I'm like, I don't remember. Well, I actually just sit in Colorado making stack-ups. So hard gold is your Enig, I think, or is it soft gold?
I don't remember.
I'm sorry.
I don't remember either.
Yeah.
That's okay. We don't have to know everything, Teresa.
NAPEG is actually a little bit more than just gold too.
So with that, I would like to thank everybody who hung out with us today. It was a long webinar with a ton of useful information. If you have any questions, please email teresa@royalcircuits.com, or you can contact me, mhughes@aapcb.com. We have another webinar a week for the next month and a half. If you enjoy these and you'd like a custom webinar, please feel free to contact me at mhughes@aapcb.com. This webinar, along with the copies of the slides, will be posted at royalcircuits.com/blog-2020 within 2 business days. And with that, Teresa, I would like to thank you so much for all of your time and expertise. It's a pleasure having you on. Thank you, everyone.
Thank you.
Have a great day, and we'll see you at the next Tech Talk Teach Thursday. Bye.